modern STATCOM is a shunt-connected device that is comprised of an IGBT-based voltage source converter, connected to the transmission grid via series-connected phase reactors, and a step-up power transformer. A STATCOM can act as an inductive device, absorbing reactive power from the grid, or a capacitive device, producing reactive power to the grid. The basic operating principle of a STATCOM is that it produces a voltage waveform in sync with the transmission system voltage. When in the inductive mode, the voltage waveform generated by the STATCOM is smaller in magnitude than the grid voltage, thereby absorbing inductive reactive power from the network. When in the capacitive mode, the voltage waveform generated by the STATCOM is larger in magnitude than the grid voltage, thereby generating reactive power to the grid. So how does the STATCOM generate these waveforms that control the reactive power output? The basic building block of the STATCOM is the valve submodule. Each submodule consists of a pre-charged DC capacitor, a high-speed switch, and electronic boards for protection and communications. Typically, there are 5 to 8 submodules stacked together to form one valve module. Several modules connected together form a complete valve for one phase of the STATCOM. These are generally stacked 3 high to form a 3-phase system. The high-speed switch that is in each submodule is actually a set of 4 power electronic devices called insulated gate bipolar transistors, or IGBTs. These 4 IGBTs are arranged and operated in a configuration that produces a positive, negative, bypassed, or blocked state. Starting in the blocked state, the submodule output voltage is 0. Turning on IGBTs 1 and 4 results in a positive output from the submodule, creating a positive step in the waveform. Turning on 1 and 3 or 2 and 4, the submodule is bypassed and our output returns to 0. Turning on IGBTs 2 and 3 results in a negative output from the submodule and a negative step in the waveform. Adding more submodules in what is called a modular multi-level converter configuration, we can generate a smoother sinusoidal waveform of the desired amplitude. To achieve this, the control system sequentially turns on each submodule to sinusoidally grow the total voltage of the converter in the positive half cycle until the peak. It then turns them all back off sequentially to bring the waveform back to 0. The control system then changes the IGBT configuration to generate the negative half cycle and turns on each submodule sequentially as before until the required negative amplitude is reached, and then turns those all back off again. One full sequence produces one complete cycle of a sinusoidal voltage waveform. By adding even more modules, we are able to achieve a smoother waveform closely matching the system. Stacking the modules 3 high, we can now produce a complete waveform for each phase of the 3-phase system. The sophistication of the STATCOM is that it is continually monitoring the always changing system voltage to maintain its output relative to the changing input. Simultaneously, the STATCOM is rapidly providing either inductive compensation or capacitive compensation when required by the system. This complete process allows total control over system compensation and helps to maintain grid stability and boost efficiency.